Good evening. I'd like to call this meeting of the Board of Public Works to order, a special meeting with only one item on tonight's agenda, and that is the public forum on the proposed landfill expansion with a focus on the contaminant transport model. We're glad that all of you are here. It's good to see a good turnout. We have with us, of course, the Board of Public Works. We have members from Citizens United who are co-sponsoring this, as well as Paradise City, and we're also happy to have the mayor here with us too tonight. If you haven't received a copy already, there is an agenda that describes what's going to happen tonight, but we'll open up with just a few introductory comments. We'll move on then to presentations by the two technical experts that are here today, and we're very happy to have Dr. Peter Shanahan and Dr. Robert Newton. We'll then open the floor up for general questions, and the meeting will be moderated by Annalise Fanza, who is here with us. We'll have an hour and a half of general questions, and then we'll have specific questions by the members of the Board of Public Works toward the end of the meeting. I just want to open up by saying that this is the first of what I hope will be several forums on the potential landfill expansion. This one, as I mentioned, is focused mostly on the groundwater transport model. And so this is what you'll hear about today. We'll have future forums on the health effects study and on the option study that are coming. I also want to say that this meeting has many purposes. The Board of Public Works wanted to have an open public forum like this for the purpose of seeing a discussion with the experts to help inform us on our decisions about going ahead with a special permit for the landfill expansion. We also wanted to hear all of your thoughts and opinions too, and hear your concerns, and perhaps there will be some new issues that will be brought up at this meeting that we're not aware of. We also, of course, wanted to create a record that the City Council can refer to by virtue of this taped broadcast. So without going any further, I want to give Linda Hessinger a chance to say a few words as well as a co-sponsor.
Citizens United for a Healthy Future would like to thank everyone for attending this important forum on vital water issues. It's on contaminant transport modeling, and it's also on some of the contamination that has been found in various tests by the city's consultants. We hope that tonight's forum will provide an opportunity for everyone to hear information that will be useful regarding the critical water issues. In addition to the precedent-setting waiver, if Northampton's regional landfill expands, it would be the first in the state to exempt a landfill from a water supply protection district. From the Berkshires to Boston, landfills are banned from water supply protection districts because landfills have the highest contaminant threat rating to the water supply. There are many issues surrounding the proposed expansion of the Northampton regional landfill over the Barnes Aquifer, such as the environmental contamination issue, the issue of environmental injustice for the people who live in the vicinity of the landfill, the health issue, and the issue of finance. Citizens United for a Healthy Future would like to take this opportunity to request that the next public forum regarding the proposed expansion be about finances. The city plans on taking out bonds for millions of dollars to pay for the expansion of the regional landfill. The residents of Northampton alone will bear the burden for repayment of this debt. The city is proposing a tremendous financial risk that will ride on the backs of residents for decades. We ask the Board of Public Works to work with us to set a date to provide the next public forum so residents can hear about finances regarding the proposed landfill expansion over the Barnes Aquifer. Thank you.
Welcome, and thank you for coming out this evening or for watching at home to learn more about Northampton's landfill expansion proposal. My name is Daryl G. LaFleur, and I'm the regular moderator of the Paradise City Forum. Over the past month, our advisory committee has worked with the Northampton Board of Public Works and the Citizens United for a Healthy Future in order to bring you this talk on regional water issues as they pertain to the Barnes Aquifer. I'd like to thank them as well as Drs. Robert Newton and Peter Shanahan for participating, and finally thanks to NCTV for recording this event. Our purpose as a public discussion group in general is to educate the public and to provide a venue for communication among people interested in Northampton and the surrounding area. We have sign-up sheets going around the room if you would like to register for our online email digest or for our traditional mailing lists. For those watching at home, there is more information on this topic and on sign-up procedures available at our website, paradisecityforum.net. I invite you to join our ongoing conversation of Northampton's past, present, and future. I also would like to point out the emergency exits. You probably all came in one of these two doors. If you go out that door and take a left, there's an exterior door there. If you go out this door and take a right, and then another left, there's another exterior door. As well, the restrooms are out to the right, up the hallway a little ways. For tonight, we invited Annalise Fonza to moderate our discussion, and she accepted our invitation to guide the proceedings of the evening. Annalise Fonza is a PhD candidate in the Department of Landscape Architecture and Regional Planning at the University of Massachusetts Amherst. She plans to complete her dissertation in the upcoming year. Her dissertation project is titled Troubling City and Planning Discourses, a womanist's analysis of 45 years of planning in Springfield, Massachusetts. Annalise has been a moderator with the Paradise City Forum on numerous occasions. In the Springfield area, she worked as a legislative aide to Representative Benjamin Swan of Springfield, and she has shared her voice locally in community radio in Springfield and Northampton at Valley Free Radio. Prior to moving to New England, Annalise was an ordained minister in the United Methodist Church. In 2002, she was appointed as pastor to the First United Methodist Church in West Springfield. In a few short weeks, she will be relocating to South Carolina to accept a faculty fellowship at the J.J. Wright Institute at Claflin University, a historically black college in South Carolina. I now turn the floor over to Annalise Fonza.
Good evening, and thank you, Daryl, and thank you to the Paradise City Forum for inviting me to moderate this important event. As usual, it is a pleasure. And I tell it's pretty hot in here. We may have to, I don't know if there are windows or anything, but it's pretty warm. So hopefully we can all get through this meeting without too much trouble. In just a few seconds, I'll introduce our panelists, but I want to say again how the format will go. After the panelists have had both 30 minutes to speak each, we will open it up for questions from the floor. I'm going to ask that you come to the microphone and stack it at no more than 3 or 4. If there are mobility issues and you need a mic where you are, the technical support can come to where you are. So don't be afraid to sign that somehow to someone so that we can make that happen as well. For each comment, I'm going to ask that you limit them to 3 minutes. I will keep time from here and also somehow notify you that time may be up. If you run over that time, there is time for rebuttals, a couple of minutes as well, but I would ask that you would not dominate the microphone so that others would have an opportunity to speak and we can get in as much questions as possible tonight. Okay, so without further ado, I'd like to introduce both panelists. Our first presentation will be by Dr. Peter Shanahan. He is senior lecturer at the Department of Civil and Environmental Engineering at MIT, and he is also a consultant for the city of Northampton. And our second panelist, as you can see on the agenda, is Dr. Robert Newton, Smith College Professor of Geology, and he is representing the Barnes Aquifer Protection Advisory Committee, and I will leave it to the discretion of both panelists to give more information as they come to the microphone if they wish about their involvement in this project. So let us welcome our panelists as they come I would say this morning, this afternoon, this evening. So we'll first begin with Dr. Peter Shanahan.
Well, thank you and good evening. Let me start by explaining a little bit of my background and then a little bit of my affiliation. First of all, my affiliation, as you see here, Hydroanalysis is one of the firms listed. I currently work at MIT. I was a consulting engineer for the better part of 30 years, and about 5 years ago, and I guess it was a fairly benign midlife crisis, I changed my career and started teaching full-time at MIT. I'd been teaching part-time for a while before that and made a switch to full-time. So this work actually started before I was quite so heavily involved at MIT, and I still maintain my consulting practice, which is hydroanalysis. My educational background is a bit mixed. I kind of straddled earth sciences and engineering in my education. I have 2 bachelor degrees from MIT, one in earth sciences and one in civil engineering. I received a master's degree from Stanford University in 1974, and that's when I first got involved in groundwater modeling, and I've been involved in modeling of groundwater and surface water ever since. After completing my master's, I worked for about 4 years in the engineering business, returned to school, received a PhD from MIT, and then I went back out to consulting. I'm going to have to switch back and forth a little bit here as I hit the buttons on my computer. You'll have to excuse me for turning my back every now and then. Do you think we need the lights out? Is it clear in the back? Can you?
Why don't I,
Yeah, okay, that's great, yeah. Okay, well, I'm going to start by talking a little bit about kind of the background to our study. And first of all, this study was done as a part of the permitting process for the proposed landfill expansion. You're all aware that a Phase 5 landfill expansion has been proposed, and it lies within the Zone 2 of the Maloney Well, which is located in East Hampton. Because of its location, the DEP permitting process, the site assignment process as it's known for siting landfills, requires a waiver be issued. And so the studies that we did were, first of all, to determine the Zone 2 of the well. That showed that the landfill is located in that Zone 2, and then we went through and did transport modeling, and I'll explain a little bit about what these are later on. But we did transport modeling to show the potential effects of the landfill on that well. And so that was done as a part of this waiver application process. We did that model development. That has been submitted to the Department of Environmental Protection, and they have accepted that and issued the waiver. This is a bit of the chronology behind all this. I'm not going to go through all of this in detail, but suffice it to say that this has been an ongoing project. It involves several phases in which we developed various models of the groundwater system, refined those models as more information became available, and added different features to it as we got further along in the regulatory process. As far as the technical part of my talk, there are going to be 2 main parts. I'm going to talk first about the groundwater flow model, and I'll describe how we put that together and what we do with that model. And then I'll talk about the chemical transport model, and there's a slight distinction there, and I'll explain that as I go forward. But these basically follow the sequence we followed in time. We first developed the groundwater flow model, used that to determine the Zone 2, the capture zone by the public water supply well, and then after that process was done, went on and looked at the chemical transport. So, part 1. This is the project area. I think you're all familiar with it. Well, just to get sort of oriented, the oxbow of the Connecticut River is located here. The Maloney Well is located not too far from that. We're over here to the west at the Northampton landfill. And you can see the town line right here between Northampton and East Hampton. Excellent. This shows the aquifer as it's been mapped. And what you see here in this kind of greenish color is the extent of the aquifer. The yellow area is uplands, which are known as glacial till, and so those are not aquifer deposits. The aquifer is what is known as a valley fill aquifer. Basically, the glacial meltwaters, or prior to the glacier, there were valleys along the bedrock that had been carved by aquifers. As the glaciers melted and washed down sediment from that was within the ice and melted off with the ice, those sediments were deposited in the valleys as sand and gravel materials. Those sand and gravel materials make a great aquifer. Water flows through them very freely, and so what you have is these kind of long linear aquifers that fill these old valleys in the bedrock. But kind of delineating, bounding those valleys are the upland areas, and these are mantled by what is known as glacial till. This is a poorly sorted material. It would be a mixture of clay, silt, sand, gravel, and even some boulders that would have been deposited underneath the weight of the glacier. It's highly compacted rock, it's tight material, and it doesn't convey groundwater very readily. So those do not form aquifer deposits. It's only these more loose sand and gravels that fill the valleys that actually form the aquifers. Not quite yet. This slide doesn't actually show up, but one thing that is also happened in the geologic history is that after the last ice age, or at the very end of the last ice age, a glacial lake was formed, and so there was impounded water that flooded this area. Lake Hitchcock covered the area, and when you have a lake, if water flows into that and it's carrying silt and smaller particles, those particles can carry out into the lake and then settle down very gently, and you have very fine-grained rocks that form as a result of that. Basically, that's what forms clay. And so much of this area is capped on the very surface by a clay layer. And that turns out to be very important. That keeps contaminants from the surface from getting down into the aquifer. So to some extent, the aquifer is protected over much of its extent by this clay layer. And I'll show you a map of the extent of that clay layer a little later in the talk. The other thing I should point out is on this slide, this shows the zone 2 for a number of different wells. The zone 2 is the area that contributes flow, basically the part of the groundwater aquifer that contributes recharge to a well. So when you pump a municipal supply well, water has to come from someplace. Those areas get mapped so that we know we can do aquifer protection measures. We know where that is, and we can do the aquifer protection measures we need to ensure that the aquifer will be safe. And I'll show you a little later how we delineated those. Go on now. One of the things that we depended upon, and again, this is a slide in the spirit that 1,000 words are worth one picture. I don't expect you to be able to read this, but I did want to show that we consulted a lot of available information. The U.S. Geological Survey and other agencies and individuals have developed a lot of information over time. We gathered up that information and used that as part of the background to our model development. And the next slide shows some of the other information that we gathered. One of the real questions was, what was the depth of this bedrock valley, what the extent of the bedrock surface looked like? It has a topography just like the land surface, but it's been buried under all these glacial deposits. So we gathered whatever information was available to help define the extent and the character of that bedrock surface. Next slide. This shows the area that we modeled, and that is delineated by this red line. And the computer program that we used basically has a rectilinear grid. It's all right angles, so we had to go to a box area, although not every part of this box is active in the model. What you see here are some of the bounds on the model, and this green line down here, that is the surface water divide of the Westfield River Basin, and that turns out to form a natural boundary on the aquifer as well. Water on the surface on one side of the divide flows one way, on the other side of the divide it flows the other. The groundwater system tends to mirror that same process, and so this forms a natural boundary on the aquifer and was a place where we could cut off our model to the south. All of these areas that are shown in gray are the till areas, and those also form natural boundaries. Those are basically the edges of the aquifer deposits. So those were also put into the model as natural boundaries to the aquifer system. Up in this corner of the model is the Connecticut River, and that also forms a natural boundary to the aquifer. So the area that you see here is really much bigger than the area we necessarily needed to model to understand the processes we were interested in. But we went to natural hydrologic boundaries, so we captured the true hydrologic essence of the system. And one other thing that's shown on this map, it's a little bit light. Well, I think it shows up pretty clearly. This black line here, you can see tracing around, that shows the extent of the clay layer that I mentioned earlier. So all these areas inside here are covered by this layer of clay on the surface. So the aquifer is bounded on the top by this tight material through which groundwater water doesn't flow very easily. Okay. This is the model as we defined it, and one of the things that the model does, or that one does in order to run the model, is you subdivide the area into these little blocks. These are known as grid cells or cells. And what the model does is it solves equations for the flow of groundwater from box to box. And so it subdivides this whole area into this very fine grid and then does this fairly complicated computer solution of the mathematical equations of groundwater flow. Those are well-known, well-defined equations. They were developed in the middle of the 1800s, and so those in theory could be solved by hand. In practice, when you get to a complicated system like this, solving those equations by hand is intractable, and one uses a numerical model. As you can see here, there's a lot of area that's grayed out. Those are not active parts within the model domain. So those are basically inactive areas within the model. Only the parts that are shown in white and the other colors are where calculations were done. There are a number of features shown here. You see these green boxes scattered about. Those are where rivers overlie the aquifer, but where the clay is absent. So those are places where surface water can interact with the groundwater system, and we include those in the model so we properly represent that interaction between groundwater and surface water. If most of the streams in New England flow year-round, the reason they're able to flow in the summer is because groundwater discharges to them all summer long. And so there is this essentially constant interaction between groundwater and surface water. The model needs to capture that. You also see some red dots here and there. Those are where large groundwater pumping wells are located. And they include the Maloney well here, Southampton well here, and several other East Hampton wells over down south of the Maloney well. So those were all put into the model. The amount of water that they extracted from the aquifer was modeled as well. And then finally we have some blue boxes up here. That is where the Connecticut River is located in the model, and in essence we represent the Connecticut River as a certain elevation of water with which the aquifer interacts, and so that effect is captured as well. And that's really the ultimate discharge point for the water from this aquifer. Let's go on to the next one. Well, I've mentioned the fact that sand and gravel convey water much more easily than does, say, clay, a tight material. And there are kind of subtle gradations within that. So even within the sand and gravel that fills the aquifer, you're going to see some differences. Some areas are going to be a little bit looser, if you like, allow groundwater to flow more freely through them. Others are going to be a little bit tighter, have probably more silt mixed in with the sand and gravel, and not be quite as good an aquifer material. And so we need to capture those differences. That's a little bit difficult. There isn't necessarily a lot of information about that, and this is always one of the challenges in doing groundwater work in general. It's all underground. You only get data where you drill a well, and so your data are often limited. We had a number of points within the aquifer where basically at municipal supply wells where the aquifer was tested and these hydraulic parameters were measured. And so this distribution is based broadly on those data. There's a little bit of interpolation here where we've taken, a reading made at one point and applied it to an area within the aquifer, but it's a pretty reasonable representation of how this property of the aquifer varies. When we think about groundwater flowing in the aquifer, we really need to think about the terms of the energy of the water, if you like. Groundwater is going to flow, much as it does on the land surface, from uphill to downhill. And that's easiest to envision in a water table aquifer. The water table kind of rises and falls, and generally in New England it's sort of a muted reflection of the land surface. So where the land is high, the water table is going to be high below that. Down at the rivers, the water table is going to be lower, and in fact the water table will be at the same level as the river water right at the river. And so you have this flow from high areas to low areas down this sloped water table. In a confined aquifer, it's a little bit different. You're really thinking about kind of a pressurized system. The water table doesn't rise to an open level as it does in a water table aquifer, but nonetheless, the principle is the same. You're really looking at the level of water that you see in a groundwater well as a measure of the energy at that point, and the groundwater flows from areas of high energy to low energy. The hydraulic conductivity, as it's known, is the property that measures how easily water will flow under a unit of that energy. And that energy is measured as what is known as the hydraulic gradient. It's how much the water table falls in a unit distance, or the pressure surface falls within a unit distance. And so the hydraulic conductivity tells how much water will flow given that unit gradient. And these numbers that are reflected here show the different values of that hydraulic conductivity. So it's a very basic concept in groundwater flow, and so it's something we need to characterize. We can go on to the next one, I think. The other thing we need to represent is how rainwater gets into the aquifer. Rainwater that reaches the aquifer is known as recharge, and it is basically the fuel that keeps the aquifer going. You need water to go into the aquifer in order to be able to draw it out and to be able to flow to the streams and rivers during the summer. And that happens on a year-round basis, but primarily in the spring. During the wet season, you get a lot of recharge then, and there's a certain seasonal extent to it. The amount of recharge is pretty well characterized in Massachusetts as half of the annual rainfall, and so that's what we used in the model. The annual rainfall is about 38 inches. We used 19 inches per year of recharge as how much water gets into the aquifer, and so that would be, you know, if you're looking at, say, a square foot of aquifer, 19 inches going into that, you get a volume per year of water that enters the aquifer. What you see here are different colors representing different recharge rates. These rates in the kind of, I'm kind of hard-pressed to describe these colors, but this lavender, okay, I'll take lavender. That lavender color is where we have the 19 inches of recharge per year. But you can see here we've delineated that clay layer. Now, where that clay layer is located, you don't get as much recharge. The clay impedes that flow of water down from the surface, and so not as much water reaches the aquifer in those areas. And so we have lower numbers there. In fact, you can see here, this number corresponds to zero recharge. We assume that no water gets into the aquifer where that clay is located there. And in this area, it turns out that the aquifer is actually, the water pressure in the aquifer, if you like, is higher than the land surface elevation. So you actually get some leakage going up from the aquifer, out of the aquifer, through the clay. So water is actually going upwards in that area. And we represented that loss of water in this zone with a very slight leakage rate of, well, 0.001 meters per day, a relatively modest rate of leakage. Let's go to the model results. Next slide. This shows the results of our groundwater flow model. And I should mention that the model that we used is the U.S. Geological Survey MODFLOW model, as it's known, MODFLOW. It's a model that has been around for close to 30 years now. It is the accepted standard for groundwater modeling. It's used worldwide and very well documented, very well validated model. These are the predictions that the model makes, and what it tells you are a couple of things. You see a whole bunch of blue lines here. That's telling us the elevation of the energy surface in the aquifer. So it's telling us the level to which, if you drilled a well at a point, that's the level to which water would rise at that well, in that well. And it's keyed to a common datum, and these are shown in meters. So if you look here, you can see that water levels are relatively high. They're up around 80 meters here. They get down to 50s down here, 40 down by the Maloney well, and lower still. So you see a pattern where you've got higher groundwater levels up here, and flow will go from those higher levels down to these lower levels. The other thing that we did, and this is a capability of the model, is we can do what are called particle tracks. And so we basically make up an imaginary starting point in the aquifer and say, okay, if a molecule of water started here, where does it go? And the model will trace out for us, and that's what all these little lines show, traces out for us where a particle of water will go, and that way we can tell the direction of groundwater flow. Now, what we actually did here is you can trace them backwards. And so we put a whole bunch of points coming out around a circle around the Maloney well, trace those backwards to see where the water that reaches the Maloney well comes from. And so what you're seeing here, all these individual traces of flow back from the well, and then outlined in red is delineated the area from which all those little particles track from. So this is the area that contributes water to the well. This is basically defines the Zone 2. The aquifer protection well is defined under Department of Environmental Protection rules. This is the Zone 2 for the well, and you can see that the Northampton landfill is located within that Zone 2. One thing I should point out, too, is that there are some other municipal wells here, and so, for example, the Southampton well is down here. We didn't trace its Zone 2, but you can see these particle tracks, and so this is capturing water from down here. The other Southampton wells are down here, and they are capturing water from an entirely different area. So it's important to note that those have their own capture zones. Those capture zones, those Zone 2s, do not include the landfill. So we're really only talking about the potential to affect the Maloney well. Okay. That concludes the flow model. I would now like to talk about the transport model. And what we're looking at here is the transport of chemicals, and these may be beneficial chemicals or not so beneficial chemicals. So the model is capable of telling us where chemicals move, and it models a number of different processes. The basic force that's going to move chemicals in the groundwater, dissolve chemicals in the groundwater, is the flow of groundwater. It's going to carry along with that flowing groundwater, so that's the primary determinant. But as parcels move within the aquifer, there's going to be a bit of mixing between adjacent particles, so there's mixing processes are captured as well. And then some chemicals will react in the groundwater system. There is bacteria located throughout these aquifers. Those bacteria will do biological processes that can affect the chemicals, that can cause the chemicals to react, so we model those kinds of processes, as well as chemical processes that affect the chemicals themselves. So we have both chemical reactions potentially and biological reactions. And the transport model was developed to capture those different processes. There's a very large number of different chemicals potentially present in landfill leachate. It would be impossible to model them all. And so what we did is, when we were starting this study, we proposed a number of different chemicals as indicators of the behavior of larger groups of chemicals, passed that by DEP, Department of Environmental Protection, and got their approval for this particular list. And we selected a number of chemicals. The first is what's known as BOD, biochemical oxygen demand. And that's basically a measure of the organic content of the leachate. And that organic content is important because biological microorganisms, bacteria, use oxygen to consume those organics in the leachate. We measure that by what is known as biochemical oxygen demand. In essence, it's negative oxygen. It's how much oxygen would get used to consume those organics. That's important because if all of the oxygen is consumed, and this can happen, if all the oxygen gets consumed, then the chemistry of the aquifer changes quite dramatically, and so we need to know where the aquifer has oxygen and where it does not. You wouldn't necessarily expect there to be oxygen in an aquifer, but in fact, most aquifers in New England are quite well oxygenated. They get enough oxygen coming in through the water table, and so oxygen levels typically are high. They're going to be a little lower in this aquifer because of the clay layer above it, but nonetheless, there's naturally going to be oxygen present. The next compound we looked at was manganese. Iron and manganese are common chemicals in aquifers in New England and Massachusetts. They can cause problems in that they can cause staining in drinking water. I get funny orange stains every now and then on my T-shirts because my water is fairly high in iron. I'm not too concerned about it because it's actually good for me to get the iron, but it is regulated. It's what's known as a secondary drinking water contaminant because it has these aesthetic effects. The Maloney well has had problems with manganese, which is very similar to iron chemically, and so we chose manganese as a good indicator to look at for that well. We could have used iron instead, but manganese made more sense for that well. The third chemical is zinc. zinc we took as typical or representative of a number of trace metals that occur in landfill leachate. It's generally one of the highest of those, so it was a good choice in that sense. It was kind of an outlier as far as its high concentrations, but it was taken as something that would be indicative of the behavior of a lot of different metals. And then finally, we used methylene chloride. Methylene chloride is a chlorinated organic solvent. It's one of a class of chemicals known as volatile organic chemicals. And these are some of the most prevalent groundwater contaminants around. You may have heard of trichloroethylene, a solvent that is very, very good at taking grease off of metal, but turns out to be a very wide-ranging groundwater contaminant. Methylene chloride is regulated at a very low level. Its drinking water maximum contaminant level is only 5 parts per billion, 5 micrograms per liter. That's about the equivalent of 5 drops in a railroad tank car. So it's a very low concentration. A part per billion is quite a small amount of chemical. All of these chemicals that I've talked about, all these substances are affected by reactions and so forth, so they tend to get a bit attenuated in the groundwater system. And so we also considered a hypothetical additional chemical, one that didn't react, one that wasn't attenuated whatsoever, so would be only affected by dilution. So we made up a hypothetical chemical, be kind of like a salt perhaps, that would just travel in the groundwater, and we assumed that it entered the aquifer at a concentration of 1,000 milligrams per liter, which would be a fairly high concentration. So this was just sort of a generic tracer that we also added. These are the chemical concentrations that we used. At the time we started the study, we did not have a lot of information on the leachate for the landfill itself, so we went to other landfills in the area to get additional data. And you can see here that we looked at the Granby, Chicopee, South Hadley, and then Northampton landfills. And for all these constituents, if they're measured over time, you'll see some variation. And so you see here we have marked the range in the concentrations that had been reported for those. And you can see in red, I've marked the highest concentration in any of those reports. And what we did is we basically bumped those up. So if we had this 4,650, we put 5,000 in our model. So we tried to be conservative in the choice of chemical concentrations. I'll use that word conservative a couple of times. And when I say conservative, what I mean is that we used, say, conditions that would be more adverse, that would make the effect of the landfill look worse than it actually was. So if we had some uncertainty in our parameters, we used conservative numbers. Let's go. We also needed to input into the model how much leachate was coming from the landfill, and we looked at 2 scenarios. Phase 1 of the landfill has no liner whatsoever. The next 3 phases have a single liner, and this consists of basically the waste lies atop a drainage layer so that leachate can be collected, can flow through this drainage layer and into pipes and then get drained off of the landfill. Beneath that is what is known as a flexible membrane liner. We have some samples if you want to see them. This is the flexible membrane liner. People think of a plastic liner and they think of a sandwich baggie. This is much more substantial. You know, it's a 1/16 of an inch thick or better, so it's a pretty substantial piece of plastic. Below that is compacted clay, and the clay and the plastic liner actually work to kind of complement each other's capabilities as far as containment is concerned. Next slide. The proposed phase, new phase, is going to have a double liner, and basically it's the same kind of system up until the first liner here. Then beneath that is another collection system, and so that this second set of pipes acts as a leak detection system. And so we have both leachate collection and then the potential for leak detection and then clay underneath. So a much more secure setup. We actually took the performance of the 5th phase as if it only were lined by a single liner. We didn't take credit for this extra liner, but I wanted to show you that difference. Next slide. We looked at 3 possible scenarios. We looked at kind of long-term leakage from the liner, and we did standard calculations from the literature as to how much leakage would occur. And basically, it comes through pinholes in the flexible membrane liner. So very small amount of leakage. Although we modeled each part of the landfill appropriately for its type of liner. We also looked at a major failure of the leachate collection system causing a release of leachate for a period of 2 days at a relatively high rate. So we had these two scenarios, and then we modeled a third scenario, which is a combination of those. We presumed this to last 100 years. We presumed that this would happen 50 years into that 100 years, and then we looked at the effect of the combination of those at the end of that whole 100-year period. So 50 years after the catastrophic leak, 100 years of continuous leakage. Next slide. This shows you the areas that were modeled as either unlined, single composite liner. The expansion will be was modeled as a single composite liner, even though it will be double lined. Okay. The equations used to model this, we again were conservative in our choice of parameters. We also used another standard model, the hydrologic evaluation of landfill performance model, which is a US EPA model to come up with the flows. And this repeats again that we assume that catastrophic failure. Next slide. This shows the amount of flow that comes out of those predictions. Those seem like very high numbers. I mean, we're talking about 30,500 gallons per year. Well, to put those in perspective, the total recharge to the aquifer is 32.6 million gallons per year. So relatively small compared to the total amount of flow in the aquifer. Next slide. This shows our predictions. This shows the concentration of manganese from 0.001 to 1 milligram per liter. That's 0.001 parts per million to 1 part per million. This compares with an input concentration of 20 parts per million, and you can basically see that the plume is attenuated very, very quickly. And it's at very, very low levels. These are levels below what you would ever measure in normal water analyses. Next one. Zinc is similar. It's attenuated very, very quickly, and these are extremely low numbers. This is 1 part per billion to 1 part per trillion in water. Very, very low concentrations. Next one. Methylene chloride has a more extensive plume, at least as depicted here, but it's important to note that these numbers go from 1 part per billion to 1,000th of a part per billion, 1 part per trillion. So these are lower levels than you would find in laboratory analyses. The drinking water limit is 5 parts per billion, so 5 times greater than this number, and that color doesn't show up at all in this map. So we're looking at below detection numbers here for methylene chloride. Next one. This is our theoretical contaminant, and again, what this helps us understand is how much attenuation occurs because of dilution. And you can see that by this point, whatever chemical is released is diluted 100,000 to 1. Down at this point, it's 1,000,000 to 1. At the Maloney well, it was about 670,000 to 1. So substantial dilution, substantial attenuation of the concentrations. Next slide. This is a detailed summary of our results. There's more numbers than I want to go through right now with just 1 minute left, but these are available in our report, and you know, that we can make them available to you as well. Next one. Well, let me summarize. Throughout this process, we tried to be quite conservative. You can see some of the aspects of the conservatism we put into our model. Where we had choices because of uncertainty, we used somewhat pessimistic choices. The results show that there's essentially nothing would reach the Maloney well above detection limits. There would be nothing detectable at the well. The concentrations were lowered very, very substantially by the time they got to the well, and so there was no impact predicted. This was something that satisfied both East Hampton and the Massachusetts DEP, and for that reason, the waiver was granted by DEP. And I think that's it, is it? Yeah. Good. Right on time.
Thank you. Thank you, Dr. Shanahan. And our next presenter is Dr. Robert Newton. Again, he is a Smith College professor of geology. He's coming, and he is representing the Barnes Aquifer Protection Advisory Committee.
I always say, live by technology, die by technology.
I'll give you a hand in a second to help you out.
It was working in there.
No, I don't know any jokes, but since it's so warm in here, it might be a good moment to kind of stand up and stretch or do whatever you've got to do. I don't know if there is a canteen or a vending machine somewhere in this building, but perhaps you might find one in the hallway.
It's nice to see you. Congratulations.
Have you looked at the video settings on this?
No, it worked. Okay.
Will everybody take their seats, please?
Okay. Well, my name is Bob Newton, and I'm a geology professor at Smith College. And I've been working on the local glacial geology for many years. And I also do a fair amount of computer modeling at all different ranges and scales, with a lot of geochemical modeling as well. And what I'd like to do tonight is to talk about two things, about modeling, but also about what's happening at the landfill today. Because we can learn a lot about what's happening, what will happen in the future by looking at what's happening today and looking at how these models might predict that future. And I'm going to say a lot of the same things, so I'll go through it fairly quickly. But first, again, the Barnes Aquifer. It is a large body of material that provides water for 4 communities, 60,000 people. So it's a large aquifer. And, of course, parts of it were established as a sole source aquifer for East Hampton. And here's my map of the aquifer, very similar. And you can see that it extends from Westfield all the way up to Northampton. The red dots represent the same municipal wells that we just saw, with Maloney Well here, Southampton Well here, Nonatuck Park Well, et cetera, through here in East Hampton. And okay, so I tend to pace a lot, so I'll try to do this. It's hard to keep in one spot. Okay, so the aquifer is very extensive, but of course the area that we're really interested in is only this area here, and there are groundwater divides that separate various parts of the aquifer. So this part is really just a totally separate entity here, and we have sort of what I'm going to refer to as the eastern branch, and then the western branch over here. And sort of as a review, here's the Northampton, here's the area of the aquifer, the Northampton landfill. And I'd like to add that there are a couple other landfills here, and I think they are important to keep in mind. That we have, East Hampton has the Oliver Street landfill. There's another landfill over here. And this is sort of a general flow pattern of water moving through the system with the eastern branch and then the western branch. And there's some sort of hydraulic connection between the two. And they're coming towards the Maloney Well. And this is the geologic map, and as we've heard, there's this aquifer is made up of this sand and gravel with the clay, and this is the blue represents the clay, and the red is the sand and gravel. But there are some areas of fine sand here where the clay is underneath, so we can demonstrate that. Here's where the essentially where the clay is here. This is what the aquifer really looks like. It's sand and gravel that was deposited by primarily meltwater streams, maybe some subaqueous fans, but there's layering in it, and some layers are very coarse gravels. They pinch out. Sometimes they have fairly steep dips going off at different directions. So it's a very heterogeneous material. And of course, that's one of the challenges in modeling an aquifer, is to capture some of this heterogeneity and try to understand how it's put together. And to do this, to understand how the deposits are laid down, we have to go back and look at how they were deposited. This is the beauty of being a geologist. You get to go out in the field and go back to these places. So here we are in Alaska, looking at meltwater coming off a glacier. And you can see it comes off in a series of streams. And if you get on the ground and you look fairly carefully, you'll see that there's, here's the glacier here. The meltwater streams are depositing these very coarse gravels. And in fact, there's a real structure to this. There's a real distribution to this. Grain size changes in various ways as you move from the ice front. And of course, the ice front is moving. So there's lots of dynamics here. But we can, if we understand what a geologist calls the facies of deposition, then you can make a picture of how the deposits look in the subsurface. So we learn a lot about the distribution of sediments by going back to these places. And as we've seen, the local areas covered by Glacial Lake Hitchcock, and here is a digital elevation model. I've put the town boundaries here. This is Northampton here. Here's East Hampton. Here's the Mount Tom Range, the Holyoke Range. And the purple here represents the extent of Glacial Lake Hitchcock as it filled the Connecticut Valley, sort of its maximum stage of Glacial Lake Hitchcock. And we can see that the area that we're interested in here lies at the edge of Glacial Lake Hitchcock. And in fact, where we are tonight is on a marginal deposit of Glacial Lake Hitchcock. It's a delta that was built into Lake Hitchcock. So what happens when you have a glacial lake? And as we've heard, we get clays deposited. But the clays are not just clay. What you get is what's called varved clay. It's a particular deposit where it's very interesting from a geological perspective because you have clay that's in the winter deposits and you have sand and silt deposited in the summer. And this is fairly coarse material. And it does have some hydraulic conductivity. So it turns out that although it doesn't have much vertical conductivity, it's hard for water to move vertically through it, water can move pretty easily horizontally through these units. The other thing that you'll find if you go to a glacial lake, especially where there's an ice front, ice marginal glacial lake, if you take a current meter and you probe down here, you'll find places where there are rivers coming out from underneath the ice. And in fact, if you take a depth profile, you'll find that there are big piles of sand that are being deposited underneath the bottom of the lake where these rivers are emerging into the bottom of the lake. And as the ice front melts back, then these rivers leave behind within the lake this piles of sand and gravel. It's sort of the class. I don't know if anybody knows any glacial geology, but there's things called eskers, which are ridges of sand and gravel. And the classic explanation for an esker is just this mechanism, the De Geer-type esker, formed in a lake as the ice front melts back. Those eskers represent areas where you have high hydraulic conductivity. Okay, so let's look at this area. And what we want to do is sort of think about developing a groundwater model, taking these things into consideration. And so we want to look at how does the ice front, how is the aquifer formed? Well, here's the ice front, and here it is it's sat here for a long period of time. It's built up a big outwash plain like we saw in Alaska, coarse gravels, and things like that. And then as the ice retreats, the ice front retreats, and if it starts to retreat at a fairly rapid rate, it might stand here this year, and next year it's melted back to here, and next year it's melted back to there. It lays down this layer of sand, and Lake Hitchcock forms behind it, and then sometimes it might pause and build up another high layer of sand and gravel, and then the varve clays are being deposited on top of it. And so these areas, these marginal areas, turn out to be where the recharge is occurring, and then they're feeding groundwater that can exist after the lake drains through that system. So here's kind of a model of what it might look like after the lake has drained. And you have this high area of recharge here. And this would be the marginal areas like where the landfill's located. And then as you move back, of course, you have the clay, and the aquifer may thin in that direction. Some places it may get thicker. You have a water table. You have a gradient to the water table, so water's flowing this way. The only place recharge can really occur, significant recharge can occur, is where these sands and gravels are exposed at the surface, and where you have clay that, of course, you don't get much recharge occurring. And as we've seen, the water table here and potentiometric surface here, some places, as we've seen, the potentiometric surface can get above ground level, and you can actually get flowing wells. And indeed, we do have in the Barnes Aquifer, and this is next to the Maloney well, we have flowing wells. And so here's an observation well next to the Maloney well where a hole has been drilled in the cap, and without any pump or anything, the water just sprays out of the ground. It's been continuously spraying out of the ground in this area since 1982. So that's a confined aquifer. There's obviously no recharge can occur here because the only way water is leaking, moving through this system is upward. It's not going down. So these marginal areas represent the high recharge areas. Now, I don't want to go through all the details we just heard about for constructing a groundwater model, but we have also constructed a groundwater model using ModFlow and all of the same kinds of parameters, except we estimated hydraulic conductivity a little bit differently. We used a facies model to determine what the distribution of hydraulic conductivity would be, and we looked at well borings throughout the aquifer to find out where those meltwater streams existed, and they existed. You can tell where they existed because there'll be areas where the clay becomes very thin. As an example, near the Maloney well, at the Maloney well, there's about 100 feet of clay. You go 1,000 feet from there to the north, to the south west, and there's only about 25 feet of clay. And that's because there's a giant pile of sand that's built, and that Maloney well is located right on the edge of one of these meltwater stream channels. And so we included that kind of thing in the distribution in our model. Okay, and so this is a calibration of the model I'm not going to talk about. But and I don't want to spend a lot of time talking about models, but I do want to make the point is that people can make different models using the same basic input and come up with different results. This is what our results are. Taking just the conservative contaminant, 41 years moving the conservative contaminant using those same scenarios that we just heard about, and we can see that within 41 years, the conservative contaminant has a 10 part per billion concentration at the Maloney well. So in this model, you get the same sort of thing. Here's the long-term leakage, and you get up to about, I think it's 15 parts per billion in the long-term leakage for the conservative contaminant at the Maloney well. So models can produce different results. Now, I don't want to spend a lot of time on models because I think if you're making your decision based on a model, then you're going to be making potentially a wrong decision. Models are tools, and they can help direct us to what we can learn about the aquifer system. So I'm not even going to go through that. That one, last one was the transient one, and this is the combined one. But what I really want to do is I want to talk about what's happening today, and maybe look at what's happening today in terms of what those models might be predicting. Okay, so I want to talk about, this is the landfill. So this is a map of the landfill, the immediate area around the landfill, and the yellow dots represent monitoring wells, and the blue dots represent domestic wells. And I want to talk about this MWB well first. This is a monitoring well here. And I want to look at it in terms of how the concentration of contaminants has changed through time. And here's what we find, is that we go back from 1996 to 2008, we see the concentration of iron is increasing through time. Concentration of manganese is increasing through time. If we go back further in time, we see that back in about 1994, we had high concentrations. They dropped, dramatically dropped, when the unlined part of the landfill was capped in 1995. And that had the intended effect of reducing these concentrations of iron and manganese. But since that time, concentrations have gone up. And so we have to ask ourselves, why? Where are those things coming from? I think that's an important question that needs to be answered. Okay, another issue, and this involves arsenic. And there have been some issues with arsenic in domestic wells around the landfill. So what is this about arsenic? Well, we do know that landfills cause arsenic to be mobilized. The important thing to realize here is that the arsenic question does not involve arsenic coming from the landfill. It's not arsenic that someone dumped in the landfill. It's arsenic that was naturally present in the aquifer materials. And it is being mobilized by that BOD, the biological oxygen demand. The reduction in oxygen due to the degradation of organic carbon is changing the chemical parameters of the aquifer and thereby causing arsenic to be mobilized. So we know that this well here has arsenic, and we know this well here has arsenic. Now, arsenic, of course, is a natural contaminant. A lot of people in New England have arsenic in their wells. It has nothing to do with landfills, and we have to keep that in mind. And this is a map that shows where the high arsenic values are likely to occur based on the bedrock geology. You can see if you live in Maine, you've got some real problems. But also notice that in western Massachusetts here, particularly where we are located, is another area where there's a lot of arsenic. So we might expect that if we put a landfill in this area, it would be potential that that landfill would mobilize arsenic that may not normally be mobilized. And it would be dependent on the chemical constituents in the water. And so one of the things that we want to add to our model is ability to predict what the dissolved oxygen concentration is. And remember that this aquifer has a clay cap over most of it. Recharge is only occurring in marginal areas. If you add the landfill is going to draw down this oxygen values. And this is just an illustration and is not quantitative, but at this point. But something we're working on is trying to model this reduction in dissolved oxygen that's coming off these landfills, particularly these two big landfills here. And the result is to lower dissolved oxygen in this area, and so we would expect in this area to potentially have an arsenic problem. The other problem with arsenic is that we have seen through studies at other places that wherever you have landfills, you oftentimes, not every landfill, but a lot of landfills, we have these arsenic-rich iron flock deposits that form in seeps down gradient of the landfill. Okay, and in this case, it was a study done in New York, and in every landfill I think they looked at, they found this was true. that there was these seeps with an iron-rich flock in them, and that iron-rich flock was loaded with arsenic. This is the iron-rich flock, down gradient of well MWB. This is it's a foot or more in thickness. It's kind of a gel kind of flock deposit, and it's iron precipitate that is loaded with arsenic. At least one sample has shown very high arsenic in this, and we would, based on the literature, expect that this is a situation where we'd have a lot of arsenic, and that this arsenic would potentially be mobilized if it was a big flood and you washed it downstream. Could be problems. Okay, finally I want to look at this well right here, 238, and I want to look at the latest chemistry that has been done at this well. This represents chemical analyses that were a sample that was collected on April 24th, 2008. And this is the result of that. Zinc was modeled. Zinc at this well was over 1,200 milligrams per liter. 1,200 milligrams per liter. It was the highest concentration of any ion in the water. That is extremely high. Alkalinity was high. I think there's a reason for that. Iron was moderately high. The other things, and I have two samplings here, but the other thing, the earlier ones hardly show in some of these things. There was almost no zinc in that early sample and a year earlier, and now it's at that concentration. Let's look at some toxic metals from this well. Lead, 3,880 parts per billion. The MCl is 15 parts per billion. Okay, that's the 424 one. Now, actually a year earlier, it was only 8 parts per billion. But it has gone up to 3,880 parts per billion. Cadmium, 2,000 parts per billion. The MCl is 5 parts per billion. We're talking concentrations 200 times the accepted level. Arsenic here. Arsenic was 10. The early one went up to 31. Okay, well, I think the arsenic is not coming from the landfill. The arsenic is probably coming from locally derived sources, and the chemistry of the water has changed associated with the movement in of that contaminated leachate into this well. This is a domestic well, although it's not being used. So this represents a serious high concentration of leachate that's moving out of the landfill. Other contaminants. I think the one that is of some concern might be dioxane. It's at 15 times the proposed MCl. I think it is the MCl now. And the thing about dioxane is it's extremely mobile. It can move through clay fairly easily. So I'd like to end my part of this by saying that the landfill represents a liability. It is a large liability. I don't know how much you read in the newspaper and news magazines, but clean water is becoming a really big issue. It is our most precious natural resource, and we can no longer take it for granted. It used to be we always had plenty of clean water. But as time has gone by, there's less and less available. Now, I believe because of where the landfill is located, in a primary recharge area, it's just not going to be allowed to have any contamination. I mean, you can never let contaminants escape. As you build up the waste in the landfill, it's got to be preserved forever. Not 50 years, not 100 years. It's got to be kept from leaching in forever. And of course, we know that's not going to, it's not going to last forever. I don't care what you put down there. It's not going to last forever. So remediation will be needed. And you know what? It'll be really expensive. It's going to cost a lot of money. And what my big concern is here is that the cost of the expansion of the landfill will ultimately be borne by our children, because it's going to be a future, it's future impact. We're already seeing that the things are happening. I think we know that given this location, it's only going to get worse in the future. Thank you. Was I short enough?